I'm going to give you two more examples on how to use residues to solve integrals. As always, the answer is going to be 2 pi I times all the sum of the residues. In this case, the residue is only going to happen at 0, right? E is always a good entire function unless you plug something bad in. In this case, you can plug in 0, and this is going to give you a problem. Same thing with sine. Sine's entire, so the only problem is if you plug into 1 over z, and you can't plug in 0 there. And similarly, we're going to see that this is the same thing. It's always 2 pi I times sum of the residues. This will just have one residue too. So I just need to figure out what the residue is of this integrand. And I can figure that out by just using power series, because I know them well. The power series for e to the 1 over z is just going to be 1 plus 1 over z plus 1 over z squared over 2 factorial plus 1 over z cubed times 3 factorial, etc. Power series for sine of 1 over z is just 1 over z minus 1 over z cubed over 3 factorial plus 1 over z to the 5th over 5 factorial minus a whole bunch of other stuff. So my job is to figure out what the residue is, and I'm going to do it by using this power series. And so I need to figure out how I could possibly get a 1 over z. Well, pretty quickly you see that if you multiply 1 times 1 over z, you're going to get a 1 over z. If I multiply 1 by anything else, I won't get a 1 over z. If I multiply 1 over z by anything, I'm not going to get 1 over z. If I multiply this by anything, I'm not going to get 1 over z. So in fact, it's going to be 1 over z plus other stuff that you don't care about. So the residue is equal to 1. The residue is equal to 0 is equal to 1. So we're done. We get 2 pi I. So the lesson, right? So if you know something about the series, you just write out the series and you multiply them out by using regular foiling type stuff. You just want to figure out what the 1 over z term is going to be, and you don't care about the rest. So similarly over here, this looks similar to one that we did on, I believe, the simple pole example. So the top is nice and entire, so I'm going to see what the bottom does. E to the z minus 1 minus z. I'm going to change that to a power series because I like power series and they're very helpful. Z squared over 2 factorial plus minus 1 minus z equals, cancel, equals z squared over 2 factorial plus z cubed over 2 factorial plus Okay, well, this is going to have a pole of order 2, or a 0 of order 2 on the bottom. So I have a little bit of a problem here because I can't just use a simple formula. But what I can do is I can write the top as a power series. This is equal to, maybe I'll put these in order, 7 plus 5z plus z squared plus, well, I know z times e to the z is going to give me z plus z squared plus z cubed over 2 factorial plus z to the 4th over 3 factorial plus This is equal to 7 plus 5z plus 1z gives me 6z plus, that's going to give me 2z squared plus a bunch of other stuff that I'm not going to need. Okay, so what I can do now is I can just do polynomial long division on these two. So, right, z squared over 2 factorial plus z cubed over 3 factorial plus a whole bunch of other stuff that I'm not going to need goes into this thing. How many times? Well, what do I need to do? I need to multiply this by 14 over z squared. If I multiply these, I get cancellation, I get 7. Multiply that by 14 over z over z squared, and I'm going to get, what am I going to get? I'm going to get like 7/3 z, and I'm going to get a whole bunch of other stuff. So when I subtract, those cancel. I'm going to be left with, I don't know, 18/3 minus 7/3 is going to give me 11/3 z plus a whole bunch of other stuff I'm not going to care about. Let's see, did I do that right? Yeah, that seems about right. So now what do I need to multiply to get here? Well, I need to multiply by 22/3 times 1 over z. Multiply this by